It's not technical by all means. So my name is Saif. I'm currently working at UWA, and I used to work at Imperial College London a few years ago. And we are the Fluid Science and Resource Division group. We are very much experimentalist group working on thermodynamic, flow assurance, NMR, and separation technologies. Okay, this is, okay, I guess. Okay, thank you. So why hydrogen? I assume for this audience, everyone is familiar why we are interested about hydrogen, but I would like to emphasize that one of the potential with hydrogen is its ability to decarbonize many several industrial sector, but also hydrogen can enable large-scale renewables integration and power generation. Why Australia? One of the main reasons is that Australia in 2016 committed to reduce the carbon dioxide to 28% below 2005 levels by 2030. In fact, some states in Australia also committed to have zero net carbon dioxide emissions by 2015. But one of the big concerns in Australia is countries like Japan, Korea, and China are also looking to decarbonize their fuel supply, which kind of also pose a threat to Australia. So we really need to look at ways of decarbonizing our fuel supply as well. In addition to that, of course, the cost of renewable energy have fallen dramatically, but also there is a lot of new science and technology and mature technology across the entire hydrogen value chain, and making this basically in a simple word nowadays it's been shifted from technology development to market activation. So we are very much really looking at constraints involved with market activation rather than just technology development. And another thing to emphasize here that Australia has very well established LNG export industry. It also has a lot of land, solar, and wind. Just to give you an idea, the population density in Australia is only 3 people per 1 kilometer square. Another issue in Australia we have is what is called liquid fuel, liquid fuel security. This is also a big thing in Australia. More than 90% of liquid fuel is actually imported, and for several times we have broken the 90-day rule that is basically set by the IEA. So this is also something really of concern in Australia. I will not go through the value chain of hydrogen. There is no time to go through that. But here I would like to emphasize that hydrogen activities in Australia is not something new. For example, in the late 1990 and early 20, we had buses that are operated and run by hydrogen fuel. But of course, if you look at the number of projects nowadays, it all basically kind of happened after after Australian commitment in 2016. We already have quite a number of demonstration projects, which I will address some of them in the next few slides. One thing to emphasize here across the value chain of hydrogen, still nowadays more than 90%, 95% actually percent of hydrogen is produced from fuel, from fossil fuel, whether using SMR or gasification technology. So while we move completely towards hydrogen production from electrolysis, still SMR and gasification technologies play a key role in this export energy industry. This is like a figure. This is a cost figure produced by CSIRO, and there is a lot of technical details behind this figure. But what is actually showing you, basically, this is the price point of hydrogen the price of hydrogen production from electrolysis and comparison with other available technologies or other available technologies. And there are a few key messages that I would like to address here. One of them is basically there is a dramatic decrease in hydrogen production price from using electrolysis. But however, that's not only like the story. There are other barrier and infrastructure problem that we need to address. For example, even by 2030, still in comparison with synthetic fuels that are driven from basically crude oil, still hydrogen is not competitive on commercial basis. However, if you look in this area here, basically by and also the industrial feedstock here, and even export, usually that things below 2025 that we are expecting hydrogen to be competitive mainly on commercial basis. Now, remote area power system is also something very important in Australia because because Australia also has a big mining industry. And they are also looking at ways of decarbonizing the mining industry and also replacing diesel with hydrogen, which basically soon will be very much commercially viable as well. There are lots of technical challenges. One of the technical challenges is just to show an example in the liquefaction. So one way we are looking at exporting hydrogen. So maybe I failed to mention here. So what is Australia interested about is basically we're not interested to produce hydrogen for domestic use, but we are also very keen looking at way of exporting hydrogen like to Japan, Korea, China, and those countries. And one of the possibilities is liquefaction. But even but the problem with hydrogen liquefaction is too light and too expensive and also too cryogenic. It's even with liquid hydrogen, it still has low volumetric density compared, for example, to LNG. And not only that, there is a lot of concern, for example, safety. There is also a way that we still need to look at better design, how to carry and transport liquid nitrogen. We need actually to address the issues with boil off rate and also special insulation, whether it's vacuum or other type of insulation materials. The other option here is basically to transport it in the form of ammonia, which is much easier and to handle. However, it is true that ammonia has also higher volumetric density compared to liquid hydrogen, but the problem is what then to do with ammonia. Because then if you want to convert ammonia back to hydrogen, then that will also add extra cost. Now, just to give you an idea, liquefaction itself is very expensive. It's very, very expensive. So there is a lot of still consideration need to be addressed, especially trying to minimize the cost of liquefaction. Here is a summary of the projects that or the activities that happens nowadays in Australia. Now you can see that we already actually have quite many demonstration projects, and majority of these projects basically actually cover the entire value chain of hydrogen. There is no time to go through this project in detail, but I'm just giving you, like I'm showing 4 main projects as an example and the potential to demonstrate some of the technologies across the entire value chain of hydrogen. Now, one good example is ColySynfuel flagship project. The good thing about this project is basically we still want to use gasification to produce hydrogen, but because of the constraint imposed by other countries, so we are coupling that with some carbon capture and storage technology, and we are planning to store carbon dioxide in one of the well-characterized geological formation in Australia. Not only that, the pure hydrogen basically will be liquefied and also will be exported. So this will give us this is like a very potential to demonstrate the technology of hydrogen liquefaction and also coupling CCS with either gasification or SMR technology. In addition to that, the phase 2 is aimed to produce high purity diesel, synthetic diesel, which is much, much cleaner and environmentally friendly compared to the conventional diesel. Another project here is Yara. This is the largest ammonia producer plant. Now, in this, they plan basically to use hydrogen generated from electrolysis and use that to produce ammonia. So that's why we call it green ammonia. And we plan to produce roughly 28,000 tons per year of green ammonia using renewable hydrogen. And then they export. Usually they use ammonia for fertilizer, but also you can use it like as in direct combustion or in ammonia-based turbines and so on. Another project here, basically they are producing hydrogen from electrolysis, but they are blending hydrogen in the natural gas grid. This is also very important and very critical to demonstrate. Usually if you mix hydrogen, so if you actually mix hydrogen with your natural grid up to around 10%, you don't need to make any modifications. But if you go beyond 10%, then there is a lot of consideration needs to be addressed. For example, the physical metering, the flow meter, the thermodynamic properties of your mixture, and whether you are going to use it in also the safety and the pipeline materials and so on. So this will be very, very good to demonstrate the potential of basically going from like 10% to finally 100% hydrogen in our natural gas grid, and to what extent modification is required. Finally, another project is called HAZER technology. This is very interesting. Here they do use natural gas, but basically they use metal ion catalysis to produce hydrogen. The good thing about this technology, which is quite recent, is you almost produce no carbon dioxide emission compared like to the conventional methods such as SMR and gasification. But also it allows you to produce graphite, and by being able to control just the operating condition in your reactor, it allows you to produce graphite at different properties. And graphite also has many industrial applications. For example, we use it in lithium batteries as well. We've also looked at across the entire value chain of hydrogen, and we kind of summarized the core ideas in terms of research and development required. There is no time to go through this, but this is also published in our website, and I assume this presentation will also be available. I just want to mention one example here, that direct use of seawater electrolysis. So everyone is talking about fresh water. That is not really the way to go from my own perspective. We have a lot of issues with using fresh water. So here there is also a lot of research need to be done in terms of using seawater rather than fresh water. Also when it comes to couple with CCS, there is still a lot of things to be done in terms of understanding mixture behavior and as well stratification in CO2, H2 stratification in geological systems and so on. Now, we've also looked at what kind of extra infrastructure required to basically accelerate hydrogen export industry, and here is again some summary. But of course, to be able to demonstrate all of these technologies, we are in the process of establishing what is called I'm sorry, I'm just going quickly to the time limits. So we are in the process of establishing what is called Future Energy Export Cooperative Research Center. This center is very much addressing two issues. One issue is countries like USA becoming producer of really cheap natural gas with really very competitive prices. So Australia is also very keen to basically still optimize the LNG industry and try to minimize the cost of producing natural gas. The other threat is basically, as I previously mentioned, countries now are looking at decarbonizing. their energy. So we definitely need basically to also establish a strong hydrogen export industry and, well, basically clean energy industry. So this is very much funded by the government, industry members, and also by universities. It's like a joint center. Again, there is a lot of information, and this is also available in our website. If you would like to know more about it, just talk to me after the session. But I only would like to end up with this slide. So the entire scope here is basically to establish a microplant LNG. So this is already in the feed stage, and this basically, by being able, for example, to withdraw some slipstream, it will allow us to test all the innovative technologies in large scale and also in real time. But not only that, we are also establishing a hydrogen train here, which will also allow us to demonstrate all the technologies across the entire value chain of hydrogen. But another scope of this center basically is also a way to demonstrate the potential of the new instrumentation, automation, and control, and so on. And there will be a lot of basically research and development center across the entire value chain. And I think I'm running out of time. Just to conclude, a remark is we believe, at least for Australia, to play a major role in terms of liquid exporting hydrogen. There is no one solution. We need to look at all different available solutions. So we definitely need to export hydrogen in terms of liquid, but also we are looking at exporting our hydrogen in terms of ammonia and so on. So there is no one particular solution. And we are talking about large-scale production. So we will still need to use like technologies like gasification and SMR coupled with CCS, while we are also expanding expanding the efficiency and also the scale of hydrogen production from electrolysis. This is our group, and this is in Perth. And here are the website if you would like to know more about this activity. And thank you very much for your attention.
Hi. Question. When you say that liquefying hydrogen is very expensive, what is very expensive?
Sorry, I didn't hear the question.
What is the cost of liquefaction that you said is very expensive, but you didn't say any number? How much it costs to liquefy?
The liquefaction. Basically, just to give you an idea, it costs more than 30 billion. So if you look at the cost of hydrogen production using electrolysis, just the production, and then you include the cost of liquefaction, it costs more than 30% compare. Usually in Australia, it's expected to cost less than $2, between 1.5 roughly to 1.9 dollar per 1 kilogram of hydrogen liquefied. That's just the cost of liquefying hydrogen.
It's coming from the electricity that you need?
Electricity, also refrigeration, and the problem with the conversion, the catalysis. Mainly the big problem with hydrogen, because you have para and ortho, conversion is like exothermic, and then basically it generates heat, which basically causes a lot of boiling off. So you need to use special catalysis during liquefaction to basically minimize that issue and to make sure all the conversion from para to ortho will be done before the final stage of liquefying hydrogen. So catalysis is very expensive, and also, of course, energy intensive, very energy intensive.
Okay. I know that Japan partnered with Australia to convert the coal to liquid hydrogen.
Yeah.
I wonder the practical progress of the project.
I think that project, I'm not very familiar. Maybe my answer might not be accurate, but as far as I know, they still basically not constructed. There is another project which is sponsored by ARENA, where they produce electricity, but they plan to export electricity by sea cables like to countries like Indonesia and so on. But the one with the Japan, not sure if to what, how advanced is it at this point.
Still in the
Yeah, it is. I think so. Yes, I believe so. Yeah, yeah. Thanks.